Hello, and welcome to the talk on subquadratic dynamic path reporting in directed graphs against an adaptive adversary. My name is Anish Mukherjee, and this is joint work with Karczmarz and Piotr Sankowski. Designing efficient reachability oracles is one of the fundamental questions in graph algorithms. Given a directed graph G with n vertices and m edges, the goal is to pre-process the graph so that given vertices S and T, we can decide whether there is an S to T path in G. In the most general case, there are only two known solutions. In one end, we do not do any pre-processing, and in order m time, using a graph search method, we can output the query. Or we can pre-compute the transitive closure in time minimum of mn and n to the omega, where omega is the matrix multiplication constant, and output the queries in order on time. A more general question is that of path reporting oracles, where the goal is to output some S to T path in G, if it exists. Again, the solutions are to not do any pre-processing and using a graph search method output a path in order and time, or to pre-compute n reachability trees in time minimum of mn and n to the omega so that any path can be reported in time order of the length of the path, which is order n. In this talk, we are interested in the fully dynamic setting where the graph undergoes edge insertions and deletions, and the goal is to maintain G, possibly with some additional data structures that support these edge updates and the reachability queries. There are several notable combinatorial trade-offs, for example, order n square update time and constant query time, or order m root n update time and root n query time, or order m update time and order n query time. Notice that all these bounds are amortized. They are also all deterministic and support path reporting. But none of them achieves sublinear update query time in the number of edges for any value of m. In fact, Aboud and Vasilevska-Williams have shown that for a fixed source target pair, there exists no combinatorial fully dynamic ST reachability algorithm with subquadratic amortized update time. Here, combinatorial means the algorithms do not use any algebraic techniques such as fast matrix multiplication. So let us see what is known for reachability using algebraic data structures. Again, there are several possible trade-offs. For example, we can have order n square update time and constant query time, or order n to the 1.529 update time and order n to the 0.529 query time, or order n to the 1.407 update and query time. All these algorithms use some kind of path counting modulo a random prime. And so, while they all achieve worst case guarantees, they are Monte Carlo randomized and cannot report paths in subquadratic time. Though, for sufficiently dense graphs, they have sublinear update and query time in the number of edges. Very recently, Bergamaschi et al. Have shown that there exists a Monte Carlo randomized fully dynamic data structure that supports edge update and shortest path reporting queries in order into the 1.897 worst case time against an oblivious adversary. That means the with high probability correctness is only guaranteed if the updates are independent of the answers produced by the data structure. For example, reporting a path may reveal a randomly sampled subgraph of G used internally by the algorithm to handle some of the most problematic cases, say the long hop paths. If the adversary is oblivious, such a subgraph typically retains its properties with high probability over polynomially many updates. However, the adversary could in principle, want to remove some of the edges of the reported paths, which could in turn break that guarantee. If these theoretical guarantees hold, even if the updates might depend on the answers, we talk about an adaptive adversary. In recent years, there has been a significant effort of the dynamic graph algorithms community to obtain solutions that work well against an adaptive adversary, possibly by completely avoiding randomization. Such algorithms are not only more general, but can also be used in a black box way as building blocks for static algorithms. In this work, we show that there exist fully dynamic point-to-point path reporting data structures with order into the 1.529 worst case update query time for directed acyclic graphs and order into the 1.834 amortized update and worst case query time in general graphs. The data structures are Monte Carlo randomized but work against an adaptive adversary. We also consider the single source reachability tree reporting problem and give fully dynamic data structures with order into the 1.765 worst case update and query time for DAGs and order into the 1.834 amortized update and worst case query time for general graphs. The data structures are again Monte Carlo randomized but work against an adaptive adversary. This is a path reporting variant of the standard single source reachability query, and there was no previous subquadratic bound known even for the case of oblivious adversary. Previously, for single source reachability, there was order into the 1.529 time bound known. We also consider the incremental reachability problem. In the incremental setting, only edge insertions are allowed. This is kind of well studied in the amortized setting. For example, for optimal query time, the known deterministic and path reporting data structures match a conditional lower bound based on online matrix vector multiplication conjecture for both reachability and unweighted shortest paths. Also, there is no subquadratic worst case update and query time possible without fast matrix multiplication. So the current state of the art for worst case incremental equals that of worst case fully dynamic, which are randomized and cannot report paths and are based on dynamic matrix inverse. In the following table, we list our results for incremental deterministic path reporting algorithms on the left-hand side, and we show how do they compare with known fully dynamic randomized algorithms on the right-hand side. For incremental reachability, we match the matrix inverse-based fully dynamic trade-offs. For exact and approximate incremental shortest path, we do significantly better compared to the fully dynamic case. And most importantly, for incremental approximate shortest paths, we achieve similar bounds as for incremental reachability. In the remaining part of the talk, we will discuss path reporting for DAGs in detail and give a brief overview of the results lifted to the general graphs. See our paper for more details on how the remaining results are obtained. We build on the following dynamic reachability data structure that support worst case update time of order into the 1.529 and query time order into the 0.529. So asking order and queries are as costly as a single update and still remain subquadratic. This has already been used for maintaining, for example, single source reachability or strong connectivity. One simple observation that we rely on is answering a reachability query does not give away any information about the randomness used unless the answer is wrong. However, wrong answers happen only with very low probability, and we consider them as failures anyway. So we show that with a single update and order and reachability queries, we can maintain a deterministic topological order of a DAG. By that, we mean with high probability, the topological order depends only on the graph itself. Moreover, we believe that this observation might be of independent interest. And notice that topological order has mostly been studied only in the incremental setting till now. And finally, given a topological order of a DAG, a path reporting query can be deterministically reduced to order n reachability queries. Now we describe the fully dynamic topological order algorithm. Suppose the vertices of G are numbered V1 to Vn according to some topological order. Consider a graph update involving an edge Vi Vj. If there is a deletion, then no update to the topological order is needed. So suppose an edge Vi Vj is inserted to G. Now, if I is less than j, then the topological order does not change. For example, if we add an edge from V4 to V5, as shown in the picture. So suppose Vi is greater than Vj in the topological order. For example, if we add an edge from V6 to V1. In that case, the vertices V1 to V6 might change their position. Now we partition this set of vertices into three sets, S, T, and Z, where S is the set of vertices that can reach V6, including V6 before the insertion, and T is the set of vertices reachable from V1, including V1 before the insertion. And let Z be the remaining set of vertices, V3 and V4. Then the update is simple. We just arrange the vertices in the order S, Z, and T. For the correctness, see that there are no edges from the set T to the set S or Z, and there is no edge from the set Z to set S. And also, vertices in the same color class do not change their respective positions due to this insertion. So we obtained the new topological order by doing this rearrangement. Importantly, only order n reachability queries are required to detect the sets S, Z, and T and to update the topological order. Now suppose a query about a path Vi to Vj is issued. Whether such a path exists can be verified using a single reachability query in order n to the 0.529 time. If so, we have that I is less than j. Now consider the following simple recursive algorithm about the path between Vi and Vj. If they are same, then we do not need to return anything. Otherwise, we go from I plus 1 to j and check if Vi Vk is an edge and Vk can reach Vj. And if so, then we return the edge Vi Vk along with the path Vk to Vj. Now, a path Vi to Vj exists, so the test will succeed for some edge Vi Vk. And the running time is of order k minus I because we have to check from I up to k all the vertices, and for each of them we need to do a reachability query. That is why we multiply it with n to the 0.529 plus the cost of the path from Vk to Vj. So inductively, the cost of the path Vi Vj is order j minus I, which can be at most n, multiplied by n to the 0.529, which is order n to the 1.529 in total. Now, for general graphs, a simple strategy would be to apply the DAG algorithm to the acyclic condensation G by S obtained from G by contracting the strongly connected components S. But the challenge is that the path reporting algorithm seems useless if G is strongly connected. But fortunately, we have the following algorithm due to Bernstein, Probst Gutenberg, and Saranurak, that there exists a deterministic decremental data structure maintaining the strongly connected components of G with order into the 2.667 total update time, which supports path reporting queries within an SCC in order length of the path time. Now, to make use of that, we need to treat edge insertions and deletions separately. The algorithm operates in phases of at most F insertions. The decremental SCC algorithm is used for routing subpaths inside the strongly connected components of the graph G minus from the beginning of the phase minus the current phase's deletions. The DAG algorithm used to find inter-SCC edges of a path in G minus. And on top of that, an algebraic order into the 1.529 plus NF time procedure is used that detects the inserted edges in the current phase that necessarily appear on a sort path P from S to T and partitions G minus into regions such that the individual subpaths of P lying entirely in G minus can be searched for in separate regions, which is very crucial. In fact, this gives us an order into the 1.529 time per update reduction to decremental path reporting strongly connected component maintenance against an adaptive adversary. And if the strongly connected components are maintained in total time Tn and can produce path reporting against an adaptive adversary, then the amortized update time of our algorithm is order into the 1.529 plus order square root of Tn into n. With the current base node bound, this gives us order into the 1.834 runtime bound. Now showing Tn equals order n square would make the algebraic part the bottleneck. And this bound is currently known to hold only against oblivious adversary. Now we describe very briefly the single source reachability tree reporting algorithm. The proposed DAG path reporting algorithm does not seem to be efficient enough for single source reachability tree reporting. So we go for a different strategy. Given a source S, for each T in V minus S, reachable from the vertex S, we choose a minimum labeled incoming edge ET from another vertex reachable from S. We show that this can be achieved after an edge update using order into the 0.235 updates to Sankowski's dynamic reachability oracle, order into the 1.235 reachability queries, and inspection of additional order into the 1.765 edges of the graph G. And again, for single source reachability tree reporting, we obtain an order into the 1.765 plus order square root of Tn into n time reduction to decremental path reporting strongly connected component maintenance with Tn total update time. So to conclude, in addition to several deterministic incremental path reporting algorithms, we obtain fully dynamic algorithms for reporting paths and reachability trees in directed graphs against an adaptive adversary with subquadratic amortized update and query times. While the algebraic data structures generally give worst case guarantees, we have used combinatorial decremental strongly connected component data structures whose update time is good only in the amortized sense. So the next question would be to obtain subquadratic worst case bounds for fully dynamic path reporting against an adaptive adversary. Thank you for your attention.